So in this question it is given that a bar of gallium arsenide is doped with silicon such that silicon atoms are occupied gallium and arsenic sites in the crystal. So how the silicon atoms are behaving in arsenic site as well as in gallium site, that we are going to calculate. Okay. Before going further, we will see what is the importance of gallium arsenide. Generally we know that semiconductors are of group 4 elements. That means they will find 4 valence electrons in its outermost orbit. The general examples are going to be silicon, germanium, okay, tin, carbon. These are the few examples, and the most popular are going to be silicon and germanium. Out of that, silicon is going to most preferred. So instead of going through directly group 4 elements, we can get a compound structure which can have 4 valence electrons in its outermost orbit by combining group 3 and group 5 elements. Like one example is gallium arsenide. In gallium arsenide, there are two metals, one is gallium, the other is arsenide. This gallium is of group 3 element and gallium arsenide is group 5 element. When it combined, the crystal is going to be consisting of 4 valence electrons in its outermost orbit of each atom. So it behaves like a group 4 element, so that it will be treated as a semiconductor, and it has better characteristics than silicon for some applications. The important applications of gallium arsenide are mainly used in microwave frequency ICs, monolithic microwave ICs, infrared LEDs, laser diodes, solar cells, optical windows, and some other applications where gallium arsenide is used. Remember that gallium arsenide is direct band gap semiconductor and silicon germanium are indirect band gap semiconductor. So that gallium arsenide is mainly used for the light emitting applications. Okay. When a recombination is taking place, a photon is generated in case of gallium arsenide, okay, which is not true in case of silicon, because silicon is indirect band gap semiconductor, whereas gallium arsenide is direct band gap semiconductor. Now come to the question. Okay. Before going to answer this one, first we will go with the known fact with silicon crystal. Generally what we know is either group 3 elements or group 5 elements are going to be added to intrinsic silicon, that means a pure silicon, so that it can be turned into N-type dopant or P-type dopant. First we will go through that one and we will get some concepts. From that one we are going to identify, okay, how the silicon atom is going to be acting as which type of dopant. Okay. So for example, let us start with P-type intrinsic semiconductor. Intrinsic semiconductor is also called as pure semiconductor, and this has a disadvantage as low conductivity, which is not useful for the practical applications. So you are going to add impurity. Adding impurity is called as the process of doping. So you can add it. Okay. You can add a pentavalent atom. Pentavalent atom means group 5 elements, or a trivalent atom, that means group 3 elements. The examples of group 5 are phosphorus, arsenic, and antimony. Phosphorus is 15, arsenic is 33, and antimony is 51. And group 3 elements are aluminium, gallium, and indium, which are 13, 31, and 49. So when you add group 5 elements, it will be acting as N-type semiconductor, and when you add trivalent impurity it acts as P-type semiconductor. So if you assume, okay, if you are going through this one, intrinsic semiconductor where every silicon has 4 valence electrons, and if you add a pentavalent atom, okay, this group 5 element is going to give one extra electron to the structure of silicon. That is, for silicon crystal, this group 5 element is going to give one electron, so that it is acting as N-type dopant. Okay, so group 5 elements are donating an electron to the crystal, so they are called as N-type dopant. N-type dopant. If you are looking at P-type semiconductor, P-type semiconductor accepts an electron from crystal. P-type semiconductor, okay, P-type semiconductor accepts an electron from crystal structure. Okay, so it is called as, okay, acceptor or P-type. Whenever it is accepting, a hole is going to be created in the silicon crystal. Accepts electron from crystal, so that it has taken an electron from the crystal towards the dopant. So there is a vacancy created in the crystal, and that vacancy is treated as hole. Okay. So group 3 elements accepts electron from crystal structure, from crystal. So there is a vacancy created in the crystal which will be treated as a hole, and it is called as P-type dopant. Now we are coming into the question. It is given that a silicon is doped into gallium arsenide crystal. Now you are going with a gallium arsenide crystal, and a silicon atoms are going to be doped into gallium arsenide. Okay, in this case you are going with intrinsic semiconductor. Either you are going to dope group 5 elements or group 3 elements, but now silicon atoms are doped into gallium arsenide. Okay, so silicon is occupying gallium, or silicon is occupying arsenide. And remember that one, gallium is group 3, arsenide is group 5. So in this case the aim is nothing but each one is going to have 4 valence electrons as a part of compound semiconductor. As a characteristic of compound semiconductor, each one should have 4 valence electrons in its outermost orbit. So gallium requires 1 electron, so that it takes, okay, 1 electron from silicon. That means silicon donates an electron to the crystal. Crystal means gallium arsenide, to the crystal. Since it is donating an electron, it is called as N-type dopant. N-type dopant. And in this case arsenide is group 5 element which has 5 valence electrons, but it requires only 4 as a part of characteristic of compound semiconductor. So it loses an electron. It loses an electron means silicon should accept that electron. Whenever silicon is accepting that electron, there is a vacancy created in the arsenide place, so that will be treated as a hole. So now silicon is able to create a hole in the crystal. That means now silicon is treated as P-type dopant. So silicon accepts an electron from the crystal from the crystal. Thereby a hole is created in the arsenide that makes silicon is treated as p-type dopant for arsenic sites, and silicon act as n-type dopant in case of gallium site. So the answer for this one is A. So the right answer is A for this one. Thank you.